All right, good morning. First of all, I wanted to thank the organizers again. I mean, we've all thanked them, but it's been really nice to have people together. For me, it's been very nice to actually give a talk in Frankfurt. I was here, but I was mostly here during the pandemic, so I felt like so it's nice to see many people in here. I felt like I wanted to say something else. But okay, let's start. So yes, I did. Interrupt with questions all the time. Yeah. Good. So I don't have so much without geometry. But let's do some geometry. Right. So this project started during the pandemic. I attended an online event with Bernd Sturmfels, and it turned out that even online, for those who don't know him, he is very enthusiastic. So even online, he can pick on people and make them talk. So that happened. So he asked a question, which doesn't have that much to do with what we're going to say, but maybe. So he had this question. So if you have some set, and he had some properties on the set, but they don't apply, maybe semi-algebraic, something like that. He wanted an algorithm to check whether this guy was reduced. Okay, what does reduced mean? Reduced means something about this object being a little bit squished in some direction. Okay, so it means that the width, that's that's what the width of an object means, like how squished it is in some direction. We'll get to that. And being reduced means that the width of S is strictly larger than the width of S prime for any S prime strictly contained in S. Okay. So it's inclusion minimal with this quantity that's attached to your object, the width. In the sense that Bernd meant the width, this is in the Euclidean world, the width is really what you imagine from the word if you know English. So your body might be kind of big in some direction, but there is some direction where it sort of lies between two hyperplanes that are as close as possible to each other. That's the width direction, right? So not this direction, and you calculate the Euclidean distance between these two, but this direction where they are very close. And this distance, this Euclidean distance, that's what we call the width. Yeah, sure. But we don't really care because we're yeah, sure. Let's say convex, but I mean, he wanted more stuff on this. Like, it's not just convex, but an algorithm for that. Okay, so he asked me, and I was like, yeah. He was like, yeah, you know width, and I was like, well, I don't know very much about this width. I know about a different width. Okay, I know about the width with respect to a lattice. And this is what I want to talk to you about. So the moving from the Euclidean context to a discrete setting where we put the lattice, the integer points into the world, and we calculate the width differently. And then basically what came out of the project is the width, the notion of being reduced for the Euclidean width and the notion of being reduced for the lattice, for the discrete width, which we'll introduce in a second, are completely different. And I can't really help Bernd with the original question very much if I study the other one. But it turned out that it was very interesting for us in a different setting. And that's where this flatness constant will come in. But it was kind of a coincidence. Yes.
If I take the lattice width with respect to the finer and finer lattice, they still converge, right?
Finer and finer.
Take 1 over n minus d to the n.
I mean, it becomes larger and larger and larger. If it becomes finer, then the width goes up. We'll see in a second. Let's give the definition. Well, I guess we won't see because I wrote it only for the integer lattice, but yeah. Yes. That's good karma. Right. So I mentioned the Euclidean width because I think this is the intuitive thing that people think about when I do introduce the lattice width, and then it can get confusing because they're different. So let's think about what this lattice width is. So the lattice width, we do the following. We take some, so you can see the black grid, right, everyone? The black grid? All right. Oh yeah, no, sorry. Now I really do have to say what objects we like to consider. Thanks, Alex. So the broadest class of objects that we want to look at width of are just convex bodies. So something which is bounded and convex. Well, kind of convex, right? Then we will have polytopes. So these are also convex objects, but they are the smallest convex set, which contains a finite set of points. So they end up being things, with vertices and linear pieces of boundary. Then we have a more restricted class. So this is the bigger class. Then we have polytopes. And then we have lattice polytopes. So in this talk, we'll mostly just think about the integer lattice. That just means the points with integer coordinates. So here we say that a lattice polytope, probably not true, I'll cheat maybe. But in general, by a lattice, we just mean an affine, or let's stick with linear transformation of the points with integer coordinates. Okay, so something that looks like a grid, but maybe modified. So a lattice polytope is a polytope with vertices, these points here, with integer coordinates, or lying in the lattice of your choice. So if you see this black grid, which is less visible than that black grid, this object would sort of be a lattice polytope. Okay, so back to the lattice width. We can define it for any convex body. So really in the broadest class. But then the examples I draw are lattice polytopes because it's easier. Right, so what you do is you pick any lattice direction. And if we were doing a general lattice, we would have to pick it in the dual lattice, which is not zero. And what you do is you look at hyperplanes, like all translates of the hyperplane defined by this direction, and sort of see what right-hand side the translates of this hyperplane can achieve on your convex body, right? So that just means you take the scalar product of your direction, or you apply the linear functional to all the points in your convex body, and you take the maximum of this. So how far can you go in one direction? How far can you go in the other direction? So yeah. And this is what's called the width in this given direction. And then for lattice width, we take the minimum over all directions in the lattice. For Euclidean width, here you would pick C in the sphere, okay? Like any, yeah. That would be Euclidean. And because these are normalized to 1, you would really end up getting the Euclidean distance between these two things. But here, you really have to think that, like, if I take 2 times C, so I can consider, multiples of the integer direction that I chose, and I get a different value, but it's going to be bigger, and therefore, when I take the minimum, I just care about, for example, primitive direction. Okay, so the ones that are not multiples of other integer points. Great. So lattice widths. Example. What's the lattice width of this guy here? Well, let's pick a direction. Like I have to check all of the possible directions. Let's pick some direction. If I take, say, this direction here, okay, I would have to take, this is the maximum, this is the minimum. I would have to check what value do I have on the right-hand side here? What do I have there? These are lattice points. So the scalar product of an integer vector with an integer vector will be an integer, right? So I will definitely have integer values here. And since there are this many parallel integer planes, I would get, like, if I have value 0 here, I would get 1, 2, 3, 4. Of course, this is assuming that I'm choosing this and not this vector. Yeah? So the primitive vector. So in this direction, I would get 4. Can I do better? 2. I thought I could do better. Yeah? 1? Yeah. Isn't this 1? This is 1.
Middle lattice point, the uppermost edge would have a.
You're right. Excellent. 2. And you can't, you're not going to be able to do better than that. But this you have to check, right? I mean, it's not directly obvious. No, you don't. This is on the same, is it? No, yeah, this is right. This is right. Okay. This guy, one more example. This is a more important example. You have this interior point here. It forces you to have at least 2. Because any plane, if I take a translate through this point, it can't be the maximum or the minimum. And then, you know, we need to have integer values at the extremes, and so you get at least 2. Good. So in this direction, you get 2. You can't do better because of this interior lattice. So this is really a certificate. Same thing happens here. Yeah. Down here, same thing. Another way I could see it is, well, I can find this guy in here. And the width, if you think about it, can only go up if I take something bigger, right? It is monotone. But so it's at least 2, but we the same direction that I drew over there sort of certifies with 2. Okay. That's what the lattice width is. And now I give the same definition that was there. And I say that K is lattice reduced if for any K prime, which is strictly contained in K, the width, the lattice width, this is the last time I'm going to actually put the lattice in here. I might probably also say width instead of lattice width, but I really usually just mean the lattice width. If the width of K is strictly larger than the width of K prime. So what I said is that it's monotone, but it's weakly monotone. So we definitely know that if I'm taking the maximum over something, if K is bigger, strictly bigger, okay, this maximum will be at least as big, but it could be the same. But here I'm saying that it's lattice reduced if instead we have strict inequality. Yes. I mean, convex body. We really want to define it for convex bodies. For convex bodies, this is not going to be an integer. certain, or not necessarily, but we really want for the more general class. And K prime is also. In fact, that's a very good question. You should talk to Kyle about this. Right. So the stuff I'm going to talk about is joint work with Ansgar Freyer, who's now with us at FU Berlin. But I kind of want to hint at stuff that we are sort of currently working on, which is more on this side. So Kyle is working on it, and maybe we'll hint at stuff that I'm also working with my master's student, Katerina, so you can talk to them if I fall asleep after this talk, also otherwise. Right. So these are our definitions. And it turns out that we can, so Bernd was asking for an algorithm to calculate, to check if something is lattice reduced, if something is reduced. And what I could tell him is that I do have an algorithm, and it's quite simple, to check if something is lattice reduced. But as I said, they do behave very differently. So that's because, oh, thought I could fit it here, but I can't. That's because we can show the following. We have K, our usual convex body. It is lattice reduced if and only if we have these nice conditions. First of all, it should actually be a polytope. And sorry, actually, there's an and, but this already shows anyone who's heard of reduced in the Euclidean setting that we are way in a different world, because people working in convex geometry, working with this notion of being reduced, are hunting for polytopes which are reduced. So they're very hard to find polytopes which are reduced. In fact, I think pretty recently, maybe 2 years ago, they found the first three-dimensional polytope which is reduced, and for higher dimensions, there's no idea. Okay, so instead, what we show, and it's not hard to show, is that if you are any convex body is lattice reduced, it automatically has to be a polytope. Okay, and we have this condition. So for every vertex of what we now know is a polytope, there exists a direction which is a width direction. So it's one of the ones that achieves the minimum. Yeah. We call it width achieving, which such that the value at that vertex is strictly larger than all the other values of the polytope, all the other points of the polytope. So what is that saying? Let's see if I can put this up and this. You can't see this, can you? Can you? Can you? No. So let's look at the example and see. So what are all the directions in which this guy achieves the width? All of them. So there's this one that we drew in red, and I've lost my red. Whatever, I'll draw it in green. This direction, if that's maybe the 0, I just put the vectors there. There's this direction. Of course, they're negatives. There's also these directions. And that's it. These are all the width achieving directions of the of this guy. What I want is that for every vertex, there is one of these directions assigned to it where this is the unique maximizer in that direction. And for this cross polytope, I can do it. I can pick the standard basis vectors, and they really select uniquely the vertices. And this makes sense that this guarantees that your lattice reduced, because anything strictly contained will miss one vertex, and that will force the width in that special direction for that width, for that vertex to drop. But it is actually an if and only if. This guy, the width directions are really just these four, but they select whole edges. And in the cube in general, they select whole faces. So there is no direction selecting any vertex, and this is not reduced, which, by the way, we knew because the definition said we want anything strictly contained in there to have smaller width, but these have the same width, and this is contained in here. All right. Good. So we've done the definition. Now, who cares? Right. That's what I want to talk about next. Are there questions, though? Sorry, yes.
That example, if I take the hyperplane in the direction 1, 1, I do get lattice with 1, right?
Yeah, these are all on the same line. Yeah, okay. I drew it very poorly, but yes. If you do it correctly, good. That's what I thought originally, but I'm sorry for my poor drawing skills. Thank you. That's it. That's as far as it goes. Okay. Yeah, some more.
Actually, so if you know a vertex is not achieved, then you remove it to get something smaller, or?
Yeah, sure. I mean, you can cut off. I mean, it's constructive to a certain extent, but we do have algorithms to take your guy and like construct a lattice reduced guy, but it's not unique. Like there are multiple ways you can go about it. So there's not like a unique lattice reduced thing inside. In some sense, yeah. Okay, so yeah, so there are two directions in which we went. One is just, so this is a well-known property that's very studied by convex geometers. And when Ansgar Freyer sort of joined the team, he was more aware of this world. And so we started looking at sort of checking analog statements to what was known in the convex world and sort of seeing how far off we are. And we're usually very far off. And it's quite interesting to see this, this difference. The other thing is that, I mean, I started off for like just by chance because Bernd asked this question, but it turned out that it was very related to something that I had been studying for a long time, and I was very excited about that. And this is the other direction that we went in, which is using this notion of lattice reduced to investigate the what we call the flatness problem that I want to introduce now, I think. Yeah. So I won't go too much into the analog of convex properties direction. So on to flatness. So we call a convex body is hollow. We say that it's hollow or lattice free, depending on which community you live in. If the interior of K does not contain lattice points. So these guys are not hollow. They all have this one point in the interior. That guy, if I see what I drew correctly, which I don't really, so it should be hollow, right? You can have points on the boundary, many, many more than vertices, but they should not go into the interior. And there's a theorem, which I like very much. It's called the flatness theorem, which sort of says the following. So if you think about a convex body that doesn't contain lattice points in the interior, and it's convex, yeah, you think, okay, it can't be too big, right? I mean, like you have to avoid all these lattice points. They have such a nice grid structure. If I need to avoid them, I can't be too big. But what does that mean? Like the volume can be extremely big because you can just, like, you know, you have your lattice points, and you might take anything which is very, very, you know, large in volume, but it sort of lies between two parallel hyperplanes. But still, I mean, this does look rather bounded in some way. In what way? In the width, okay? And indeed, that's what this theorem is going to tell us. So that in some way, if you are hollow, you can't be too big. So if K in fixed dimension D, this is very important, is hollow, this is always a convex body, then there exists some constant that depends on D, so it's a constant in dimension D, such that the width, the lattice width, look at that, I remembered, is bounded by this constant. Okay, so this is a theorem due to Kinchin from the 40s. But in the 80s, it was rediscovered. It was only published in Russian, so I have no idea how he proved it. But it was rediscovered in the 80s by Lenstra, who used it for a polynomial time algorithm for integer linear programming in fixed dimension. Very fixed dimension. So people were very excited because this is a big deal. The thing is, you don't actually determine the best possible constant here, okay? You get some bound, but you don't know if there are really, you know, hollow convex bodies that are that wide. In fact, you know, the original constants were incredibly huge, the original upper bounds. But knowing where we actually are, like what the actual bound is important also for these applications, right? So people really cared about what is the real value of the flatness, then you can just make your algorithms more efficient. And asymptotically, actually, now we're doing pretty well because what the trivial bound. So what do you have to do to really know that something is the best possible? Well, you need to show that anything with a larger width cannot be hollow, so that this is an upper bound, and then you need to construct something which is actually that wide. Yeah, the trivial lower bound is always D, because you can dilate a unimodular simplex. It's going to be hollow, and it has width D. Sort of standard simplex, make it multiply it by D. And now we know that the asymptotically, the upper bound is D log D, or not quite log D, some polylogs, blah, blah, blah. But this is a recent breakthrough, amazing result. But we've been steadily going down from like, the original things were super exponential. Then we had quadratic, which was a breakthrough, and then like slowly decreasing, and now we're like, you know, yeah, we finally know that it's kind of linear. Exactly. That's what I want to talk about next. So what we like to think about is, what about for small d's? The only one where it's known is d equals 2. This is due to Herkins. And for d equals 2, the real constant, so the actual best, is 1 plus 2 over square root of 3. Which tells us, of course, that the maximizer is not. So the polytope really realizing that is not a lattice polytope at all. Has strange number there. But I can also use this board. I never thought about that. That's why this was so hard. Now we're golden. Okay. It's different. Strictly different. No, I wouldn't say that it's necessarily easier. It's different. So for d equals 2, it's 2. So the unimodular simplex is the best. For d equals 3, it's also 3. So not just the unimodular simplex, but other things as well have 3, and you can't do more. And higher than that is not known. Yeah. Right. So if you have a convex body in a certain dimension, which does not contain interior lattice points, then its width is bounded. Okay. The problem is that the theorem is not constructive, or rather, you prove the theorem by finding some. The proof somewhat constructive, but you don't find the best possible constant. You just get some upper bound, which is valid. I mean, everything that has larger width is not hollow. But the question is sort of, how small can I make this number? Exactly. So to understand that, what do we have to do? We want to say something about the class. What can we say structurally about the candidates, or the polytopes that we hope, or the convex bodies that we hope realize this largest possible width, which exists because everything is compact. So I mean, there is going to be something which, oh no, we were saying that we should go over there. I know why I'm here, because I have this thing and now I have to hold it in my hand. Don't know if I need it. Right, so if you want to tackle the lower bound, so you want to understand really what do the guys that could possibly maximize the flatness constant look like, you need to start thinking about their structure, right? So the first thing is the theorem due to Lovász. The accent goes this way, okay? In 89, which says that. I'm going to cheat a little bit. You really, I'm only talking about convex bodies, but really you could talk about the unbounded ones as well. But let's just stick with convex bodies. So if you want bounded inclusion maximal hollow, convex bodies. So we really mean for anything, any k prime, which is strictly larger than k prime is not hollow. So it does contain a lattice point in the interior. Okay, so it's as big as you can make it. You can't add anything to it while keeping the property of being hollow. They have a lot of structure. First of all, are they are polytopes. Maybe I do it. Polytopes, not lattice polytopes, but they are polytopes. With at most 2 to the d facets. The facets are the highest dimensional faces. And each facet, these highest dimensional faces, proper faces, they contain a lattice point in their interior, in their relative interior. which means that and this is an like if you are inclusion maximal, you have these properties, and if you have these properties, you are inclusion maximal. It is an if and only if. Like as long as each facet contains a lattice point in its relative interior, you can't get anything bigger. No, it can be more than one. It can definitely be more than one. But there is at least one. So something like this is going to be inclusion maximal hollow. These lattice points, they block your facet. You can't put anything beyond this facet without capturing this interior point. So it's clear that these need to be inclusion maximal. These are all the inclusion maximal guys. Okay. So if you want to study the flatness constant in terms of finding exact values, you might as well restrict to just looking at inclusion maximal hollow bodies, right? Because it is monotone. So if you have some guy which achieves the maximum, you also have an inclusion maximal guy which achieves which achieves. And this is how this exact value is found by Perkins. I didn't write it down. I think, yeah, if I have time, I want to, not that much time, but we'll maybe get into that in a second of how he actually did that result. What I want to say is that our idea is that you can instead look at lattice reduced polytopes. So here's the cartoon of this business. Just like you say, well, if you have some guy that realizes the flatness constant, so it's as wide as you can be, then you have an inclusion maximal one, which is still hollow and has that. You can also go the other way around. You can say, well, if you have something of your maximum width, you have something contained in there which is lattice reduced. Okay, so in each dimension, this is, I guess 24 is when it's published. Editor. So realizer, we really mean this maximum, this polytope of maximum width, which achieves the flatness constant. So this is sort of the picture. If you take the poset, so of course, in general, I mean, in dimension 2, there's a unique maximizer, but in general, there could be many, many, many. You order them by inclusion. In some fixed dimension, ordered by inclusion. Here at the top, you have your inclusion maximal hollow. Any realizer, so we have a fixed width. These are all things which are hollow, they don't contain interior lattice points, and they have the maximum possible width, okay? So at the top, in terms of inclusion, we have inclusion maximal hollow, and at the bottom, we have lattice reduced. Okay. And we say, yeah, sorry? Families. I mean, a priori, we don't know that there's a unique, even at the top or at the bottom. what would be fantastic is if these two actually collapsed. So this is a conjecture that is very dear to my heart, and might therefore be very wrong. Maybe now I should go on the other side. Or maybe I should erase, yeah. I think I can't reach the third board. Right, so questions while I erase a couple boards? Yeah. Yeah, because if you want to understand all the lattice achieving directions from which you have to, check to check this thing, there is a way to calculate this quite easily because, quite easily is. The lattice with achieving directions are exactly the lattice points in the following convex body. You take your K and you take the difference body, then you take the polar, and now you shrink or dilate so that this is centrally symmetric, so it certainly contains 0, but you shrink or dilate until you hit the first possible lattice points. All these lattice points, they are the width directions. So you have to look at what's called the first successive minimum of this guy. The lattice points on there are exactly the width achieving direction. This is bounded. You can compute this, at least for rational polytopes. You can do it easily, and then you really have that finite set that you can check from, and that's how we have our algorithm for rational polytopes at least. Right, oh no, I was erasing. Here. Are we ready to part with our examples and definition?
Kind of late, but yeah.
Yeah. This is sort of the bold version of the conjecture. Then there are milder versions, but basically, exclusion maximal hollow. I mean, in that post-it, not in general, but like for realizers are the same as lattice reduced. And we have a theorem that says that as long as we're talking just about simplices, then we do have that all realizers are lattice reduced. So let me put it this way. Hollow simplices achieving the flatness, realizing the flatness constant are necessarily lattice reduced. Problem is we don't actually know if they exist, right? We don't know if the maximizer in general dimension is a simplex. But this is also a conjecture and one that I think more people rather believe that. So, oh, I can't take this off now. Damn. Yeah. Yeah, that's true, but it's not going to be contained So it is inclusion maximal. So if I take something else, like say like this, maybe.
These are all maximum, right?
Yes.
Not all of them.
Right, but here I'm not saying that this is true in general, that any inclusion maximal is lattice reduced. I'm saying that we hope that for realizers of the flatness constant, so just among realizers of flatness of D, I said it wrong probably, but realizers, that's the hope. What we can say is that, for example, if I define the flatness constant just the maximum width of hollow simplices, then the realizers are necessarily lattice reduced. This is sort of our main result, is that this lattice reduced thing really does pop up. And I mean, there's good evidence, like all the candidate wide bodies are simplices. Okay, so in dimension 2, that realizer is a unique simplex. My advisor Paco and I built something which is the widest known hollow convex body, and it is a simplex. And in dimension 4 and 5, Meyerhoff, Schaden, Weltke constructed the widest known hollow convex bodies. They are simplices and are lattice reduced. That's good. Right. So, right. I want to say, we can say a bit, so we have a result which is sort of an analog to Lovas's result, the Lovas's structural result about inclusion maximal hollow convex bodies. We can say that sort of lattice reduced things, this is in general, not just for realizers, convex bodies, as I said before, thanks to that proposition, are polytopes. With at most 2 to the d plus 1 minus 2 vertices. And the arguments really are similar. So there we had a maximum number of facets due to these interior lattice points that certified that you needed that you need in the interior of these guys. And there's something about parity classes of the coordinates of these points saying that there can't be too many. And here it's a similar argument. The vertices are certified by width directions. These width directions are points, as we were saying before, in some other convex body. And also there you can do a parity argument to say there can't be too many. And guaranteeing the uniqueness. So it's really an analog thing there. This is all, sorry. And in the last 5 minutes, I want to say a little bit about our hopes and dreams, basically. So we want to, so we wrote a project about this, and it's now going on in the SPP. That's happening, and we're very excited about it. So it's in collaboration with Cottbus, so Gennady Averkov is there. We have a new PhD student, Kyle. Yeah, we're very excited about this. And Ansgar came to Berlin, so things are happening. We're excited. And yeah, so what we want to do is we want to, so the original approach of Herkins and what you might think is, so you had this results about inclusion maximal hollow convex bodies. And you say, okay, so let's try to really look at all the possibilities for these guys. And what do I mean by that? What does Herkins do? Let me show it to you again. So you know that they are inclusion maximal you know that they are polytopes and they have a maximum number of facets. And these maximum number of facets are certified by these interior lattice points. And you notice something else, right? So, which is how you get the bound on their number. So if you take the polytope, which is the convex hull of these lattice points, This polytope does not contain any other lattice points except for its vertices. It's a strong property. These are called empty polytopes. And what does Herken say? Well, in the plane, the only empty polygons really are just this square and this triangle up to, well, you know, transformations that keep the lattice, so we don't really care. Unimodular transformation. There's only these two options for the points certifying the facets, okay? So you're either going to be, if you're inclusion maximal hollow, you're either a triangle like this, or you are a quadrilateral like this. And then what does Herkens do? Herken says, well, okay, this case, that case. This case you just do easily by hand. And you show that the lattice width of something like this is at most 2. And this he also does by hand, much less easy. But you know, not just directly, like you need some considerations. You need to say, if you're hollow, then you're avoiding this lattice point, this lattice point, and sort of the lattice points opposite of sort of the opposite edge in your triangle. So on this lattice point, and that's enough. If you can avoid these points, then you're automatically hollow. You don't need to check all the other points. This is a 3-parameter family. If you want to be circumscribed around these 3 points, you just have the slopes of the edges to choose. Then you add these extra conditions, and then you do a lot of playing with inequalities and trying to maximize width. You can show that there's finite numbers of directions that you need to check, and machinery, you show that the maximum is 1 plus 2 over square root. So what we said is, okay, so the cases which are not triangles are dealt with. We want to reprove it, but we want to use lattice reduced. Actually, we want to use both inclusion maximal and lattice reduced. What does our theorem says that you can assume that they're lattice reduced if you're just talking about simplices. If they are maximizers of the width and hollow, then they are lattice reduced. So we can really think of something which is both inclusion maximal hollow and lattice reduced. So we can impose these two conditions together. And our idea is that this will help us much reduce the complexity of these calculations and therefore be able to push it to dimension 3. So what we did, just as a proof of concept in dimension 2 again, it's not a new thing. But what we could do is we could classify. So we start on the lattice reduced side. We say, okay, we classify up to unimodular transformation. I have destroyed this chalk. Triangle. So we're in the plane, remember? All of them, not inclusion maximal, not realizing the flatness constant, just all of these. And they need to look something like this. You have these width certifying directions, and you have a single vertex. So for each vertex of your triangle, you are on one of these hyperplanes. And well, you need to really hit all of these hyperplanes, so one needs to be on both. And you can sort of then just take a transformation and say, great, so our box, let's let it really be a box. We have some extra inequalities about where these 2 points should lie. And this, of course, is the width. So these are hyperplanes that achieve the width. We can force them to sort of be on a box, be the standard lattice directions. And then we want to impose also being inclusion maximal hollow. We want to say, what's the largest this can be such that I can still put on top the lattice and stay hollow? So I need to be able to say, I will have something like this imposed on top. And combining these two properties, instead of just having the inclusion hollow significantly reduces the complexity of the calculation. Yeah, and I should probably stop. The problem in higher dimensions is that a lot of the things that we've said, so like, for example, just for simplices, we need to have at least these three, and then for tetrahedron, we need 4 lattice points. But there are infinitely many empty tetrahedra, not just the unimodular one. In the plane, there's just the unimodular one. So that's already like, okay, we hope that we can really say if you have things which are not unimodular inscribed in there, you're far off, but something that we need to prove. And so there are steps that need to be taken that Kyle, Ansgar, and I are working on. Gennady. Yeah, but I guess that's a good place to stop.